All right. Okay, it's recording. So yeah, again, I'm back. My name is Don, and today I'll talk to you about steps to reproducible research. So how many of you know, kind of heard of like reproducibility, right? It's good to have a reproducible research, but sometimes, some people might not know what is reproducibility. Well, in a single sentence, reproducibility is the ability to exactly recreate earlier research or analysis given the same data. So meaning that if I hand off a piece of journal that describes my method for research and the input data, another person can make the exact findings. And that is very critical, right, in research. So I've came across this great article in the Science magazine of just this, actually it's just great figure where there's this reproducibility spectrum. So just by the way, this tutorial is in the schedule. So the link is in the schedule if you guys want to follow along. But in research, you have publications, and sometimes you just put out papers, and that's it. And then somebody comes in, read your paper, but then they're not able to really try it out for themselves. You're lacking in data. You're lacking in the actual code method that you did. But then there's this other spectrum of like full replication. So you have links to your code, you have links to your data and everything. And it's just like the full replication. It's like, you have a frozen machine on the cloud where somebody can just go in, run your simulation, and get the same exact thing. This might not be also, the best thing ever because, your research is your own work. You don't want somebody to kind of steal your work, right? And so we want to find this kind of middle ground of just a balance because you don't want a full replication. You want a reproducible research where somebody can try it out for themselves, but you don't want them to just steal your work and, get their names in the lights after you've done all the work. So I'm going to have a little discussion. If you guys actually could go to the link. So just from the Geohackweek schedule website, just click on that link, Steps to Reproducible Research. And then down below on this reproducibility discussion, there is a link to Etherpad that we will discuss. So what measures do you take to ensure that your analyses are reproducible, replicable, and robust? So let's just take a moment there. Hope everybody is able to access this URL. So just under each of those things, if you guys can just fill in there what you think.
What's the difference between replicable and reproducible?
So I don't know. What do you think? Let's see what you think of what the differences are. Let me see. Everybody is able to access that? No? So yeah, the link is this reproducibility discussion, and then there should be an Etherpad link here where let's just get an idea of, what measures do you take to ensure that your analyses are reproducible, replicable, and robust? And there might be a little confusion between reproducible and replicable, but let's see what you guys come up with. reproducible, DOI to code, DOI to data. It's really cool because DOI is a very unique identifier to get at your code and data. Accessible data, detailed methods, not using set W in R. I'm not an R person, but cool. What's set WD? Oh, okay. That makes sense. Include well-commented code, unnecessary dependencies. Let's see if anybody mentions all of the different tools that we've actually learned this week. Now I'm using Conda to describe my environment. It's great. Jupyter Notebooks. I see some of the tools mentioned here that we've learned, which is really great. And then for replicable, include code, GitHub references and papers, writing comments, README files, Docker. Very cool. It's definitely would allow a person to really replicate what you have. Instructions, great. And then what makes a robust? Unit regression tests, which is really great. That's what Joe talked about earlier, having really robust tests. And dry, don't repeat yourself. Tox, detox. So tox is just another testing framework. Malicious, fully reproducible. All right. Well, these are great discussions. I'll leave this in here. We'll probably add it to my next time I give this talk. All right. And just a shameless copy that this is actually from a earlier Hack Week, Ocean Hack Week that happened like 2 weeks ago. So bear with me. So yeah. So Ian, right? You asked different, ask what's the difference between reproducible and replicable. Well, reproducible, you have, say, you got your code, and then you have the instruction how to run your code and how to do your method, and you have your data there. But then there's you can't, a person can't just take those code and then just know kind of the nitty-gritty configuration that you've done, right, to exactly just run the code and then get the same exact result as you did, right? Replicable is then, somebody can just take what you've done, say you have a virtual machine, and then they can just install that virtual machine and then, boom, run it. They don't need to think about any setup. Then, they can just get exactly, the method and then the data and then get exactly the result that you have made. But that's kind of like I said earlier, you kind of want to find a middle ground between reproducible and replicable in a way that you don't want another person to just steal your work, right? Because you've worked on it and it's your baby, and so yeah. So there are these simple steps to just reproducible research. So one is record the project's provenance. So how many of you have heard of the word provenance before? Okay. And those that don't, just provenance is just basically a history of what you've done. So it's kind of like a Git is a form of provenance. So every single changes that you've made is kept in a history so that you can go back later and then and track. So there's what's called a data provenance where you know what your resulting data, what comes in, what other data comes in to create that data. So it's the changes, and you can go back to the original input data set that you've used for your research. So that's the notion of provenance. And then data and metadata curation. So make sure that you have a very rich metadata that that bites to some standard depending on your research and depending on your field. And then establish a testing analysis workflow. So this is what Joe did, right? He established a very great testing workflow for his project and his research, and that is definitely a very important step to have a reproducible research. And then next is test, document, publish your code. I know this is like a little bit repeating of testing analysis workflow, but having a test and then document every single piece of your code is very important. And then publish your code to, say, GitHub, right? And then, so in GitHub, there is an integration to what's called Zenodo, where you can actually get a DOI for your repository for each release that you have, so that then you can complete the steps to reproducible research, which is share it. So then with those DOIs, you can just share it with somebody, and they can discover your code, and then they can try out their try out your methods or whatever functions, tools that you have created. But for this tutorial, I'm not going to cover record or the metadata curation or establishing a testing workflow. Those those vary depending on your field and research. So you guys have your own testing workflow, your own metadata curation, and the provenance. So, but I am going to cover how to test, document, and publish your code. So it's pretty much how to create a Python package 101, but a very robust, or like very reproducible, robust Python package. Why am I doing this? Well, in research, experiments results are not trusted unless the experimental setup is tested, the method is well documented, and 3, we can demonstrate that our results are reproducible and reliable. So why would a scientific software be any different? Well, clear code is paramount. So just enjoy this nice little comic. Have you ever had a time where you just given a code and then you're like, ugh, I hate this code. There's no documentation. This is ugly. This is like, very confusing. And then you end up spending tons and tons of hours trying to decode someone else's code, right? Before you even use it in your own research. And that's a waste of time. So it is very important that you have clear code. And then also good practices for scientific environment creation is also important, right? You don't want to have this script that does pip install, easy install, brew install, npm install, and all this different stuff. It just is just a madman, right?
Is that? I don't know enough about environments to know why that is like really bad.
Well,
What are they doing in this?
So it's like you have all these different steps that can be very confusing if somebody comes in and, say, trying to tweak a little bit of something, right? And then, there's all these different installs. Well, what if you use a different computer? It might not work, right? So you just want to have one kind of workflow way. Maybe just have a Docker, and that's it. And, the Docker will take care of everything else, like all your installation and all your configuration, all that. So let me introduce you to the code, test, document, publish, cookie cutter. So I know that this week you guys have been creating code to do your work and whatnot, and you might wonder, how do I make this into a package where I can share? Well, I've made another cookie cutter. Yes, it's another cookie cutter for the scientific Python package, but my thought is that this is a smart cookie cutter. It is another standard, it's another thing out there, because there's a lot of cookie cutters out there for scientific Python. So what is a cookie cutter? It's just basically a boilerplate, a template where you have the different pieces to make a good reproducible Python package. So what we'll need is this package that I have developed about 2 weeks ago. It's very new. Just disclaimer here, it does not work on Windows yet. I have not have support for that. It needs to be on a Mac or a Linux machine, unfortunately. That is in the works of making it run on Windows. But yeah, this is the cookie cutter. So for this cookie cutter, I follow the guideline of the UW eScience Institute guidelines for reproducible and open science to create the structure of the package that's needed. And then you'll need a GitHub account. You have that. And then you'll need a Travis CI account. I'm not gonna go over on how to create a Travis CI account. I'll probably send some resources on that. Or Joe, you can probably send resources on how to create a Travis CI account. So how many of you have created a Python package before? Like a full-on Python package that you can install. Okay, great, 1, 2, 3, all right, awesome. So you guys know kind of what the steps are to creating a Python package and how much of a headache it is, correct? Yeah, so yes, creating a Python package is not easy. You know, there's many different steps and many different things that you need to take into account. So I'm just gonna pull up a package that I am developing currently. Let's see here. So just as an example, this is a package that I am developing as my current job. It's a package that helps you get ocean data using Python. So as you can see, this is a Python package. Has many different pieces, right? So what did I do to create this? Well, at first, you create a folder. You create a Git repository. So the things that you've been doing all along, right? I create a folder called YodaPy, and then I make another folder called YodaPy. In that folder, that's where my code actually live. And then after that, to make a package, a Python package, you need what's called setup.py. Just to show you how ugly and complicated setup.py is, you can see here. So you have what's this function here from setup tools, right? And in this setup tools, you have all these different variables. You know, you can specify the name, the version of your package, and then description of your package, and then all the different dependencies can be listed out here. Install requires, and then you specify what dependencies. So the dependencies is like what tools you're using. So if you're using pandas, GeoPandas, you want to specify that. Just to make it clean, I basically just grab this install requires from the requirements.txt file. So let's go back and look at. So requirements.txt file is like an environment file. It's usually used if you want to install like pip packages, right? But you can also use requirements.txt to install packages into Conda. So this is just another way to do that. So this just lists out all the different dependencies that my package requires so that I can install it. And when I do like pip install, it'll try to grab all these different other packages, right? So, and then, so that's that step. And of course, there's a step of choosing a license. So GitHub has many different licenses that you can use. So I chose MIT license, but there are other licenses. So you just need to read up on the different licenses. So I gave a URL there. Or did I? I did not give a URL. I will give a URL on the choose a license, but there are a listing of licenses, software licenses that you can use to make sure that you're the owner, and then depending on the license, you want to like give rights for somebody to like copy and contribute or not do that, all right? So you have that. And then so the third step there is write doc test. So let's see, doc test. So that's just documentation. So you have just the documentation of your packages. So I like to use what's called Sphinx, right? So this is just example of Sphinx. It's a different syntax. It's almost like Markdown. This is called the REST text. So yeah, so that's kind of, I don't have extensive documentation on this yet, but ideally you want a well-documented thing. And then doc test, so the test, so documentation and test, that's what the doc test means. So you have tests, right? So I'm not gonna go over this, but basically if you remember earlier from Joe's talk, he's written really robust tests for his functions, so you want to do that. And for me, it's just, I'm using PyTest, so just very simple test. I have a function for each of the, I have a test for each of the function that I use. Not as fancy as Joe's, but it of course is more simpler library. So that's depending on your use there. And then if there's a bug, then you want to fix the test and rerun. And then of course you want to set up Travis. And then so in order for you to set up Travis, you need to create a Travis account. And then for Travis, so Joe didn't mention this, but in your repository, the way Travis knows to use this repository for like, pull request and then test every time you make a pull request is this .travis.yaml file, right? So this is where you specify Travis and like, hey Travis, read this, and this is what you have to do to test my packages. So as you can see, this is complicated, right? I mean, it took me a while to actually understand what's going on here. And, for scientists, like, there's just so many things that you got to keep track of. And, like, this is just another thing that you have to learn. So, I mean, there's documentation on this, but, I just want to go in and start writing code. I don't want to have to worry about this. I want this to be kind of set up. Well, that's what the cookie cutter do, right? I have just a baseline of a package set up with Travis, YAML, all there, right? So now, more of the interactive stuff. I know I've been talking for a while. Let's go. So for those who doesn't have a Mac or Unix machine, you can just use the Jupyter Hub. So I'm going to use a Jupyter Hub because I'm using Windows here. Oh, and another thing, actually, just to show you. So another cool thing about Sphinx and automatic documentation is you can make something like this. So this documentation was created straight from GitHub. So this is just another project that I was involved in before. So this is created from the docs folder within my GitHub. And then the cool thing about Sphinx is that you can have what's called doc strings. So doc strings is documentation within each of your function, right? And then Sphinx will render that into this nice formatted thing where then somebody can go in and they can see what functions are available, what variables are available in my function, and how to use that function. And you can just put it in there. If you don't believe me that this comes from code, you can see the source and see it's just that, right? In your code, in your def get affiliations or whatever, that's just an example. You type in, what does your code do? What are the arguments that it expects, and then what do I return, and then just give some examples in there. So with Sphinx auto documentation, you will get a website like this that is straight from GitHub, right? And you have a nice documentation of your code. All right, okay, now actual interactive. All right, so let's open up a terminal. Why isn't the terminal opening? Well, that's not good. Okay then. Sorry guys. I opened this like earlier and I got kicked out. Hopefully this doesn't take too long. Yay. Okay. Now it should work. Perfect. Maybe? Yes? Okay. So let's do pip install. So my package name is called rppc. And let's try it. It'll just pull all the different stuff. Let me just look at the package.yaml. Okay. Now split windows here so that I can see both things. Okay, so first thing to do with rppc is you just install rppc, pip install rppc. You should get the latest version, which was released last night. So I did a bug fix on the Git under the hood. Okay, so for me, so I want to create a new Python package. So I just create a package.yaml. I love YAMLs. It's so simple. Okay, just in your text editor, open up, I don't know, name package.yaml. And then what it requires, what rppc requires, is the name of your package. So I'm gonna do my Geohack package. Yeah. All right, just a little description. So description, can you guys all see this? Okay, yeah? All right. So I'm gonna go slow so that everyone can follow along. This is a package I've created. It's awesome. Okay. And then its author. So currently I can only do one author. So I'm gonna just put my name, my first and last name, and then put email so that somebody can contact me regarding my package. I don't know, at uw.edu, right? And then dependencies. So this is like, what libraries do I use to create this package? So I don't know, I use pandas. I use GeoPandas. I use Xarray because it's so cool, and I use Folium. All right, let's just play with that. And then now the GitHub ID. So this will allow you to be able to connect with GitHub later. So make sure you actually use your actual GitHub ID here. So I'm gonna use my GitHub ID. So let me know if you guys are following, if you're caught up or not. You guys all caught up? Yep. Good, good, all right, awesome. So now let's save that file. So now I should have a file called package.yaml. So in order for you to run the command line that I have is called rppc init. So if you're not sure, you can do rppc -- help just to see. So this is just the help, just to see what's available. So if you're not sure about init, so the only argument here that is available at rppc is init. In the future, there will be many features that I want to put in here, but this is just a very simple. And then rppc init help will show you within rppc init what are all the different arguments that I can do. And I see that there's like info file. So you want to do rppc init -- file, and then now specify that package.yaml file. And then I want to upload this to GitHub, right? So this will create a Git repository for you. It will then upload to GitHub if you choose to do so. If not, then you have to manually upload it to GitHub yourself. But if you choose to do so, do a -gh. Oh, just one warning though. If you have a two-factor authentication set up on your GitHub, you have to follow this instruction to create a personal access token to use this. So this might be, it's just a little extra step. I haven't put in a functionality where you can just automatically do that yet. But say I choose to upload to GitHub. Okay, going back to my script here. And then, oh no, it is not working. Dependencies, did I misspell that? Yeah, it broke. Did I misspell dependencies? Okay. It's one of those things. Dependencies. Is that correct spelling now? I hope. Live demos. Okay, that looks right. Okay, let's try it again. All right, so now it'll give you the step of choosing a license. So there are documentation on like what each of these licenses mean. I'm not gonna go over that. So let's see. I'll try, I don't know, BSD3 clause new. Not quite sure what that is, but I'll try license number 9. Okay, so then it's gonna ask me, what is my GitHub username? I know if you've already put it in there in the other part, but this is actual like login to GitHub. So we'll enter your GitHub password. So I'm gonna enter my GitHub password, and then once this is done, as you can see here, it's doing a lot of different things on the back, right? So let's actually look at what it's doing. Okay, so what is it doing for me? Okay, first, initialize empty Git repository. So this is what we learned about first day, how to initialize a Git repository. Second, it uses what's called versioneer. So versioneer is really cool, that in a way that it actually knows, put automatic versions for your package. So if you make a release on GitHub, it will version your package as that release. So, and then each of the commits, it'll be like a weird, it'll add a version plus the commit string, the commit hash string. So it set up versioneer for you. And then after that, it creates documentation. So this is what this doc source, all this stuff here, creates the docs folder and the documentation, the Sphinx documentation. And then it puts in all these different stuff. So like you have Flake 8, right? So Flake 8 is a linting service. So linting, it just checks for your code quality. So if, say, you're like, I don't know, having too much spaces or whatever, it'll like check. And then if you ever try to run a test on your code quality, then it will fail on you because like, hey, you're not meeting the Pip standard. So Pip is a Python standard. So as you're programming in Python, if you don't meet any of those standards, that means your code is bad, right? I mean, it might not fail on you and you still be able to run your code, but for readability and for reproducibility later on, like I said, always make sure you have a clean code, right? You don't want to hand off your code after you're done with your PhD to someone else and poor someone else having to like read your messy code. No, that's not good, right? And And so it creates all this stuff. And then see right here, my Geohack package. So that's the actual package. Creates your init file. And so like now, if you look at your actual folder, see right there, there's my Geohack package, my Geohack package. So I want to install it. So there's nothing in this package right now. But just to show you that this is a complete Python package, you can do pip install -e. So -e will allow you to, it's like a development mode for pip. So like if you do pip install -e into your package, then as you make changes to your code, you can import and things, like it will propagate those changes into your installation of your package. So just pip install -e dot, and then it should do that. I have some error, because of my, I've created, I did not space that, so that was my bad. But if that error is not there, it should install it. So yeah, let me just fix the error here. So this is in setup.py. Yeah, it's not completely smart enough to escape the error. Okay. Did I do another one? Oh, it's awesome. Yeah, thank you. So it's part of those things. Okay. All right. It'll try to pull the dependencies. It might not work because I have a lot of different dependencies. But yeah, so you can pip install -e your package. See, it's pulling all the different dependencies. Oh, it actually works because in the Jupyter Hub, all those dependencies are already available. So yeah, there you go. So now I want to run a Python console. So I can import my Geohack package, and voila. See, now then I can do my Geohack package dot, I don't know, run raster analysis or whatever function that you have in there. But it's all complete, and that only took a few seconds, right? It's very easy to create a Python package. So now let's go to GitHub and see if it's there. So I'm going to go to my account, or you can go to your account. My Geohack package is right there with the licenses that I want. And yep, so there it is. I have all this different stuff. So all these different pieces are actually, these are the best practices that I've found. Talking with colleagues, consulting with eScience, just all the different pieces for this. So like, you have the .travis YAML set up for you for your package. Right now I have just a very simple test set up for you. So this is an example of a test. Hello world. Then you can look into more of like how to create tests, but that's not part of this tutorial. But yeah, so you have that. You have your docs. In the future, there's, I'm the sole developer along with another friend of mine right now. But in the future, I want to make this more robust and more functionality of like, automatically create that documentation that you saw earlier, online documentation of your code, and then, connecting that to Travis right away. So that's kind of the future direction of this. This is just my little project that that hopefully you guys find it useful and you try to use.
Is there the steps you just did to create a package? Are those steps available in your Git or RPC?
Not yet. I will expand that. Thank you. Yeah. So I'll create a little documentation of the different steps, and then so that you guys can try it out at home. Yeah. And if you are like a pro Python person and you know how to create packages and all that stuff, feel free to contribute to this. I want this to be a community-built package that helps, just scientists to get started in writing code, because it's hard and it's overwhelming, and there's a lot of different pieces and you might not know, but with the community helping each other, this is the foundation of open source. So, yep, thank you, and that's all I have for today.
Thanks, Don. Any questions or comments?
Nope.
We got one back here.
Yes.
Well, if any of y'all are coming down to the SCG annual meeting in Anaheim, California, we're going to be putting on what we're calling a reproducibility zoo, where people are going to be nominating papers on an app, and then we're going to have like a hackathon going on during the annual meeting, where we're going to be just reproducing landmark results in geophysics. So please, if you find yourself in Anaheim, then come on down and collaborate.
Cool. Good. All right.
What does Docker do?
So Docker, it's another beast. It's a containerized application. So Docker allows you to, let's actually go to the group that I've been involved in the Geohackweek, actually have used Docker for their project. So it allows you to have, like I said, replicate what you have, just any workflow that you have. So this is the web portal group. So they have a Django Web Server, but this Django Web Server, you have Django. So this is the step to installing that Django Web Server, right? This is the configuration. I need to install the environment, and as you notice here, there's environment.yaml. So they need to install the conda environment needed, and then set up the server. So that means doing the environment and then whatever other Python scripts that they have to put, they put that in there. And so then when you do what's called a Docker run, then you can, it creates this virtualized instance of your application. And that way then I can just, in Docker, put an input, and then a Docker can run a script or whatever, and then it can spit out the output without, messing around with your computer.
Okay.
Right. Say, there's still some kinks in Windows with Docker, but, say you have just the steps of workflow that you need to be done, and rather than you going in and doing each workflow like that, you can do that in Docker. You just it'll just run whatever that you need in there. And then you can really customize your configuration of your machine in Docker. It's just another visualization tool. Yeah.
Okay.
Hopefully that makes sense. Docker is like a whole beast.
Yeah.
So.
Well, because when you download the Python API for Google Earth Engine, it
Yep.
asks you to download it. I have it. I just don't know what it does. Which is great.
Oh yeah, the Google Earth Engine Python API, it comes with a Docker, right? You can install it using Docker, and then you can run it that way. And within that Docker Google Earth Engine Python API, it has kind of the setup for you, so that you don't need to find how do I set up the credentialing, right? But then I think Tyler shared that there is a Conda Forge. In Conda Forge channel, you can install the Python API, right? But then you still have to know how to do the authentication with Google. So, yep, it's yeah. All right, cool.
Thank you.
Thank you. Good luck on all your projects.
All right, thanks, Don. Well, I think what we'll do is go to lunch a little bit early, give us a little more time, and let's really try to be back here right at 1. It would be great. We can do the survey. Mostly, I want to make sure, I know some folks want to get out of town or have travel plans, like so that we can get to that 3:30 deadline, or finishing up the projects would be really great. So let's just try to start right on time at 1, have a good lunch, and we'll see you back here in about an hour and 20 minutes.